This video is on work, which is defined as force times distance. So here I have a trough that's filled with water, and I want to find the work done in pumping the water out over the top of the trough. So here's the water trough again, and so it's 5 feet this way. And then across here is 2 feet, and then across here is be 3 feet, and then the height here is 2 feet. And so once again, we want to find the work done in pumping the water out over the top. And we'll make the assumption that water weighs 62.5 pounds per cubic foot. And what I'm going to do is this water here, I'm going to divide it into 8 slices like this. So we have 8 slices of water. And then we're going to move each slice over to the top. And then we'll find the work done in moving each slice of water to the top. And so here is slice number 1. And so to calculate the force for this slice number 1, then we need the volume of this slice. And then the volume is going to be the distance from here to here, which we'll call the width. And then the length is going to be 5 feet. And then the thickness of this slice is 0.25. For this first slice right here is 0, and right here is 0.25. And so I'm going to use the average distance, which is right in the middle, right here, as the distance from the ground for this first slice. And then now for the width, we need the distance from here to this line right here, this line. And therefore we need to know what is the equation of this line, so that we can figure out what the width of this slice number 1 is. And so notice that this point right here, this is the point 1, 0, and this is the point 1.52, because the distance from here to here is 3. So right in the middle right here, from here to here is 1.5. And therefore this line right here passes through the point 1.52 and the point 10. And therefore the slope of this line is going to be 4. The equation of this line will be y minus 0 equal to the slope times x minus 1. So we end up with y equal to 4x minus 4. And then now let's rewrite this as x in terms of y. And we get x equal to 1/4 times y plus 4. And so for this slice number 1, as I said a few minutes ago, we're going to use the midpoint right here as the distance from the ground. And so right in the middle right here is 0.125. And therefore, when y is 1.25, then x, to find the corresponding x, and then we replace y here with 0.125. And that will give us an x of 1.0313. And so the distance from the y-axis to this line right here, at y equal to 0.125, is 1.0313. And therefore the width of this slice of water is going to be 2 times the 1.0313, which is 2.0625. And then the length here is 5, and then the thickness is 0.25. And therefore the volume of this slice of water is 2.5781. The weight of this slice of water will be the 62.5 times the 2.578125, which gives us 161.1. For this slice, the distance from the ground is 0.125. The distance from here to here is 2, and therefore to lift it to the top, to lift this slice of water here to the top, it will have to travel a distance of 2 minus 0.125, which is 1.875. And so here we have the force or the weight of this water, and then times the distance that it needs to travel to the top is 1.875, and that will give us 302.12. And therefore the work done in pumping this slice of water and moving it to the top is 302.12 foot-pounds. And here's slice number 2. And right here, this is y equal to 0.25. And then right here, this is y equal to 0.5. And then right in the middle is 0.0375. And I'm going to use this number right here, 0.375, as the distance from the ground for this slice number 2. And therefore, this right here is 0.375, and therefore the corresponding x using this equation right here is 1.0938. And then multiply by 2 to get the width of this slice number 2. It'd be 2.1875. And then the length is 5, the thickness is 0.25. So the volume for this slice number 2 is 2.7344. And so the weight for this slice number 2 is 170.89. And so the work done in lifting this slice to the slice of water to the top here is going to be lifting it from here to here, which is a distance of 1.625. And so the work is 277.71 foot-pounds. And so that's for slice number 2. And then for slice number 3, the work is 248.41. Slice number 4, work is 214.23 foot-pounds. Slice number 5, the work is 175.17 foot-pounds. And then slice number 6, work is 131.22 foot-pounds. And then slice number 7, work is 82.39 foot-pounds. And then the last slice, which is slice number 8, the work is 28.68 foot-pounds. And so the total amount of work done in pumping the water, all of the water out over the top, is going to be, we're going to add all of these values together, which comes out to be 1,459.96 foot-pounds. But we got this answer here by dividing this trough of water into 8 slices. And so to get the exact answer, we need to divide this into an infinite number of slices of water. And so when we divide this trough of water trough here into many slices of water, then here is one slice. And let's call this slice the ith slice. And so the distance for the ith slice, the distance from the ground to the slice, let's use the midpoint right here, and we'll call it y sub I star. And therefore the distance from here to the top would be 2 minus y sub I star. And the distance from the y-axis to this line right here is going to be 1/4 times y sub I star plus 4. And so the width of the ith slice will be 2 times this. And then simplify, we get 1/2 y sub I star plus 2. So this expression here, that's the width of the ith slice. And then the length again is 5. And then we'll make all the slices have the same thickness, and let's call the thickness delta y. And therefore this is the volume of the ith slice, and then to get the weight for the ith slice we'll multiply by 62.5. And here of course we're making the assumption that water weights 62.5 pounds per cubic foot. And therefore the work done in lifting the ith slice to the top of the trough is going to be the weight times the distance. And so the distance would be from here to here, which is 2 minus y sub I star. Once again, y sub I star is the distance from the ground to this slice of water. And then simplify everything, we get 156.25 times minus y sub I star squared, and then minus 2 times y sub I star plus 8, and then here's delta y, which is the thickness of the slice. And so to get the exact answer, we need to allow n, which is the number of slices, to run to infinity, and then we get this limit quantity right here. And then again, when this limit right here exists, then it becomes we defined it as the integral from 0 to 2, 0 to 2. And then here we get negative y squared minus 2y plus 8, and then delta y. And then the integral for negative y squared is negative y to the third over 3. And then for negative minus 2y, then we get negative y squared. And then for 8, we get 8y. And then evaluate from 0 to 2, we get 1,458.33 foot-pounds. Recall that at the beginning of the video, when I divided this water here into 8 slices, and then calculate the work for each needed for each slice, then we got 1,459.96 for 8 slices. But here, for an infinite number of slices, we get 1,458, which is very close. And that's the end of the video.